This is Science in Parallel, and I'm your host, Sarah Webb. In this episode, I'm speaking with Stephen Wilson of Arizona State University. Stephen completed his PhD there in 2024 and has continued to work as a postdoc in chemical engineering. He and I discussed how his research evolved from experimental to computational work, how his 10-year experience in the Navy shaped his career, and his advice for the marathon of completing a PhD. Stephen's graduate research was supported by a Department of Energy Computational Science Graduate Fellowship from 2021 to 2024, which we refer to as CSGF for short. This podcast is a media outreach project of that program. Stephen and I spoke in July at the CSGF's program review in Washington, D.C., an annual gathering for fellows to network and present their research. Stephen, it is great to have you on the podcast.
Thank you, Sarah. Yeah, I'm very glad to be here.
So, first of all, for our listeners, let's just start with a really kind of high-level elevator pitch of what it is that you are currently working on.
I'm a postdoctoral fellow at Arizona State University in chemical engineering and in the Munich lab group. So I'm a computational chemist by trade. So I do, as it sort of sounds, chemistry on the computer. And I look at chemical reactions and various different chemical properties using computational means. So my current work is actually, my postdoc work is associated with plasma interactions and reducing iron ore with plasma and looking at if we can make that a more carbon neutral and energy efficient process.
Great. So I want to kind of take a step back and learn how you got into doing all of this. Where did your early interests in science and engineering come from?
I did have an early interest in science. I was usually generally pretty good in math and science growing up. Really early on, my dad got me interested in science with this you make your own rock crystals kit type of thing. And so from then on, I was really interested in science in all aspects. I actually fell a little more in love with astronomy a little later on when I went to a natural observable laboratory. I saw Saturn for the first time. And so then the scientific field in general sort of stemmed from there. And then my path sort of grew from different aspects into where it is now.
Great. I know before you got into research, you spent time in the military. How did that happen? Tell me a little bit about kind of your career and where it started.
Yeah, I enlisted in the Navy right out of high school. And that's sort of where my career really started. I joined the Navy nuclear program, which is the longest enlisted school you can go to and one of the most difficult. You sort of learn nuclear physics and thermodynamics and everything in a really short period of time. And short period of time meaning about a year and a half, roughly. And then I had some extra training to become what's called an engineering laboratory technician, which basically just means I did the chemistry for the reactor and radiological controls. And so in all, it was about 2 years of school. And then from there, I go out and serve in the fleet. I was on an aircraft carrier and out of San Diego, and then various positions from there over a 10-year span.
So all over the world, I imagine?
Yeah. So station-wise, I was in San Diego, Washington State, and South Carolina. But where I visited I was what's called a Westpac. So it's the Pacific or Eurasia ports. So Singapore, Thailand, Hong Kong, Dubai, Bahrain, lots of places.
Wow. So what do you think were kind of the most important things that you learned either scientifically or personally from that experience?
The Navy experience really allowed me to grow. I was, maybe as most people that are good with math and science, a little awkward, a little not socially adept. So the military experience in general plunges you into that kind of world. But scientifically, because I was still working with nuclear power, I got to really keep my interest in the science not in academic fashion, right? So I was still learning a lot of new things every day. And then growing all these really what some people call soft skills, time management and stuff, but in a military sense, it's very accelerated, very fine-tuned. There are strict time requirements, there's a strict uniforms, everything's strict. So you really develop this strict, rigid character about yourself.
Well, thank you for your service.
Thank you, yeah.
And so you finished up your time in the Navy. What led you to chemical engineering?
chemical engineering sort of aligned with what I was doing in the Navy. So again, as an engineering laboratory technician for the reactors, I was maintaining chemistry and radiological controls. That was my basic training. But as in a 10-year work career, essentially, I worked up the ranks, and I was actually at much higher levels of engineering operations, maintenance, and everything in the equipment, achieving eventually what's called engineering officer of the watch. So you oversee everything in the reactor plant and mechanical plant operations. And so from an engineering aspect, it's a large plant system and all these different moving parts. And so I knew from there I wanted to do engineering, and then I knew I wanted to do chemical engineering for my background in chemistry, and it sort of married the two perfectly.
Okay, so chemical engineering. Did you know that you wanted to do research, or was that something that came along the way?
I did not know I wanted to do research. So not in my first year. I knew it's a hard transition going from military to academia, especially. I think I was 28. I think I was 28 at the time, starting undergrad. So a very different path. And I was just learning the first year, just that transition and going into school. But it only took about a year before I realized I sort of wanted something more than just the run-of-the-mill, take my classes, do my homework. I wanted to see what else was involved, and that's when I started looking for research opportunities.
What was your first research opportunity?
The first one stuck, I guess you could say. I played around with the idea a bit, but the first, I talked to a couple professors at Arizona State. So I did my undergrad at Arizona State and my PhD. And that's because I met my PI the same year he actually started at Arizona. So Chris Muick was just joining in 2018. He was looking for undergrads to sort of start facilitating his lab and other aspects of it. And so we hit it off right away, I think.
Did you start working on then sort of the fundamentals of what you're working on now, or has that evolved over time?
It's definitely evolved over time. So in Chris's group, I actually started in the lab. So not a computational at all, really, because he was starting to grow his lab. And with my background of already 10 years and knowing how to work certain equipment and construct lab equipment, in a sense, I helped him build some of his actual experimental lab work until he got his first PhD student and then some other people that came on to do the experimental side of things. And that's when I transitioned to computational, because that also did interest me. And that's where I've sort of been, I don't want to say stuck, but that's where I've been since, and have enjoyed it since.
So talk about the computing part. Where did computing come in for you? And was that something that was an interest all along? I'm sure you were dealing with computers when you were in the military as well.
Yeah, the way I use computers now is very different than I did in the military, and very different. So I grew up, I'm millennial, I guess is the term, right? And I grew up without computers until maybe I was in my early teens, I guess, is when I first started interacting with computers. And, I was actually asking some people in my lab group recently, do they still require like Microsoft Office as a class in high school? Because for me, it was one, right? And they said, no, they don't, it's not a requirement. But in any case, this is the first time when I started at ASU and in Chris's group that I really understood what high performance computing was. I was very unaware of what that meant in the beginning. And then I learned how we can apply it, and we sort of marry this idea in computational chemistry, anyways, physics and chemistry, which are both, again, very deep scientific fields and interest me a lot. And so it still piques my interest every day as I get to look at now, not just one chemical system or one chemical compound on an experimental side and become an expert in that, but I can become an expert in a lot of different chemistry. It doesn't have to just be one specific type. And so that's the exciting part of computational chemistry.
So you're talking about this evolution, though, from being an experimental researcher to a computational researcher. What led you into that trajectory?
Yeah, so that it evolved with my PI's lab. So he brought on a PhD student that sort of took over the experimental side of things, and now he had the gap on the computational side. And so I've sort of been that person because I've been with him I've been with him the longest in the group of everybody that's in the group. And so I've always been the person to sort of fill that role of something that he needs along the way, because I've always been interested in something new. I'll learn something a lot, drive it as far as I can, and then not exactly switch gears, but apply everything that I just learned from that one specific system to this next gap that he wants to fill. And that's sort of how it evolved into computational chemistry from experimental, and then in the computational chemistry side from one topic to the next.
So you're the utility player who pushes the envelope?
Kind of, a little bit. His lab's grown a lot since, so there's a lot more utility players out there. But yes, I've done a lot of that.
Or it sounds like maybe that's partially your interest and skill set, maybe.
Oh yes, I always yes. I'm curious about everything, which can be a bad thing as well when you can't focus on just one topic. But I do like to look at everything that I possibly can.
That sounds really great, though. So let's talk about a couple research projects. I guess maybe let's talk about your PhD research first and kind of, give me a sense of kind of what you focused on during that time?
Yeah, so in a broad sense, applying computational chemistry, I looked at how do we more efficiently find materials for a specific chemical reaction, in this case, something called chemical looping, where you take a material and in a cyclic fashion so you can recover it, drive a reaction that gives you products. In this case, we wanted to form hydrogen fuel from essentially steam and sunlight. And then you can use that hydrogen fuel for either storage or a lot of different things for hydrogen you can use for hydrogen. But then you can keep doing that reaction over and over and over again. And so my goal was to build a high throughput process that can more efficiently find or optimize materials for that chemical reaction. And there's a lot of different avenues that I did trying to find that. But that's the overall.
So what were the challenge, or maybe pick a particular challenge that you had to overcome, or how did you sort of work through the process of finding answers to your questions?
Yeah, so the overall challenge was that at every part along the process of finding these materials was a human interface, which can slow things down. It becomes sort of an Edisonian approach to, I need to try this material, change one thing, try it again, change one thing, try it again. And that's not conducive to high throughput and trying to span thousands of materials. It can take years. And so one of how I look at things is I like to make things more efficient. It's really troublesome to me when I look at something and I can clearly see some inefficiencies somewhere. And I'm terrible in traffic. I'm terrible standing in lines because I can always see, or at least what I think is a more efficient way of doing something. And so it really bothers me. And so the first thing I looked at was the way we model these thermodynamics for these materials. And the thermodynamics are sort of what govern how well it will perform in the given chemical reaction. And so the very human approach was that you have to design a very specific model for the very specific system. So one chemical compound that you're looking at, and then you have to do that. You have to change that model for every chemical compound. And so I wanted to see if there was a different way where you can take a more broad model and apply it to several different chemical compounds so you can get their thermodynamics over thousands of materials and compare them more efficiently, more quickly. And that was the very first one.
What's the status of that work? Are you still working on it?
So yes, right now, I still work on it a little bit, but someone in the group has started, actually at the beginning of this year, it's sort of taking over my role as I sort of transition into refining that, what we call the CrossFit CEF. CEF stands for Compound Energy Formalism. And they're sort of trying to adapt it to be even more efficient than I made it, because everything will always become more efficient. And so right now, we've done a lot of work in showing its feasibility. There's, I think, at least three articles out there right now on it, and sort of just waiting for that field adoption. It's sort of still early in its phase.
What would you say are the barriers to adoption at this point?
It's relatively new, and it does require an adoption of the way you collect your data. This is the way the experimentalists, in their sense, collect their data. So right now, the process that they use is collect a lot of data points in a very fine grid, so very close together points that they're sampling. And then they build that model that they used to build by hand, and it's a very iterative process, and they're very comfortable with it, right? It's been maybe 20, 30 years that they've been applying this process to these materials. And so since it's brand new and it requires a shift in gathering data points that are actually far apart to fit my type of model, it can be a slow adoption, as with any brand new process.
Tell me more about what you're working on now.
Yeah. So from there, again, still efficiency-wise, building on that idea of how can we more quickly sample materials, and especially in a computational sense, we looked at using Bayesian statistics to inform people how they sample experimental data points. So a priori, you can determine what is the next data point you should sample without needing to know anything else about the system. And then from there, in my postdoc, we've started from the expediting the computational side of things with a company startup with me and my PI called SciForge, Sci being PSAI, because we're including artificial intelligence in this process. But what SciForge is sort of a wrapper around current quantum chemistry software that speeds it up and makes it faster to come to an answer. And so that way, SciForge will do all this mundane work while you can focus on the science.
Nice. In terms of the systems that you can apply these tools to, I mean, are there atomic limits? Are there chemical limits? I mean, how generally applicable?
As with a lot of the way computational things work, the simpler you make the problem, the bigger you can apply the problem to. So there's what are called either different functionals or different processes in which you can apply to thousands of atoms or hundreds of thousands of atoms. But if you want to get down to chemical accuracy, you have to change a functional, and then you're looking at maybe hundreds to 200 atoms at most. And there's a lot of different reasons for that. One is just that the way quantum chemistry works, it scales horribly with the atom size, specifically the number of electrons. And that's what SciForge tries to address, is getting around that scaling problem by expediting the computational side of things with AI. And then we don't have to worry too much about the size of the system, and then just more so now, can we get AI to get to chemical accuracy no matter the size of the system?
What do you think is next for you?
So I've been a postdoc for about a year now. In that first year, so right after I finished my PhD, my PI and I decided I was going to try and apply to academic positions. The academic and postdoc world has been a little hit heavy right now, and it's really scarce opportunities right now. And so in the meantime, this startup started, one, because this project is sort of something my PIs thought about. We thought about this for a long time, and we've been working on it here and there for a long time. And we finally decided, this is an avenue that we can pursue while we figure out while I'm still applying to things. And so we're applying for funding right now. And I mean, if it gets funded, this can definitely be my full-time thing as far as work is concerned. But I'm still looking at other postdocs and academic avenues.
Great. Good luck.
Thank you.
So a slightly broader note, I mean, obviously part of why we're talking is because we're here at the CSGF program review. And I want to learn from you a little bit about your CSGF experience and what you've learned, how that's shaped your career so far.
Yeah. Getting awarded the CSGF is probably one of the best things, I think. Definitely the best things that happened to me during my PhD. It allows so much flexibility in what you can research. I wouldn't have researched any of the stuff that I did without the CSGF. You bring your own money to the group, and so you can research whatever you want. And so there's a lot of flexibility. And then on top of just that flexibility, now you get to interact with a very unique cohort of people from a very broad range of sciences. And so you have access to just a lot of good resources between the cohort and other fellows, as well as alumni. The alumni are indispensable. They provide so much information. Just go on the CSGF Slack channel, and you'll see all kinds of people asking questions every day. So from the personnel side of things, but then the resources as far as you get to go do a practicum at a national lab, and you can do as many as you want. I think you must do one, but as many as you want that you can fit into your PhD, and you get to experience something outside of your current field, which broadening that science. And again, as I mentioned earlier, all sciences interest me. So getting to look at something different for a little bit always just excites me.
Well, tell me a little bit about your practicum then.
Yeah, I did my practicum at PNNL. I looked at, it was still a computational side of things, but I did, instead of what I currently do, which is called density functional theory, DFT for short, I did molecular dynamics studies instead. So again, using that different functional, maybe you can say, to look at water droplets of serine. And we were trying to get thermodynamic properties from computational calculations. That was under Sam Johnson. She's actually moved away since PNNL. She's at Colorado School of Mines now as a faculty, which is also exciting for her. So again, your thing with the fellowship is, you just create this network of people that travel all over the place and just open more doors everywhere. So,
and that's a lovely segue, because I'm interested in the people who you feel like have influenced your career, either people who have been active mentors, people who have been role models for you in terms of things that you've thought about in your scientific career so far.
I've had a lot of mentors along the way. And I look at mentors, I've had both good and bad mentors, or leaders, you can say. And so you take all the good things and try and leave the bad things behind from every leader that you come across. And that was throughout the military and now into my academic career. And so, my biggest academic mentor has been my PI, Chris Mioch at Arizona State. He's definitely shaped my path through academia. He's been helpful. He helped me write the CSGF package, right? So everything I can attribute to my success in academia has been through him, for sure.
What do you think has been, is there either a particular story or a particular quality about him that you think has been particularly important for you in your development?
Well, I'm a very unique a very unique background, being pretty much the same age as my PI. I think he's maybe 6 months older than me. So, or 6 or 8 months. It's not, I can't remember exactly. So it was very comforting. I wasn't just like a student to him. It was a close relationship, almost friends. You have that barrier between PI and student, but he didn't just treat you as me as a student. That would have felt very weird to me, being the same age. And I always already felt weird in classes, being about 10 years older than everybody. So I didn't have those regular group study sessions till 12 a.m. with people. I usually had my hard cut off, just being 8. You get a bedtime as you get older, right?
Right. Just exactly.
So it was comforting in his group to sort of have that. I could still have that academic relationship and not feel like I was in a weird spot. He made it very comfortable.
That's awesome. I mean, it sounds like there have been elements of feeling a little bit like a fish out of water at times, but I did a PhD too. And one of the things that I think that I very much appreciated in my own academic experience were people who had a few years away, a different set of life experiences, and the way in which those people thought about problems differently and how they brought their career experience, life experience to their science. And I wondered what you felt like your added life experience and the experience in the Navy. What do you think that brings to the table for you?
My specific experience through the Navy really gave me a lot of hands-on experience from the things that I learned in my undergrad, for sure, especially in chemical engineering. And so when I got to the point, in a common chemical engineering undergrad, there's a junior lab and a senior lab where you're supposed to gain that hands-on experience. And these were all already familiar things to me. And so the operations side of things was already secondhand knowledge to me. It was very instinctual. And I just had to make sure I married the deep theoretical side of things that I was learning to that operational side of things. And so I got what I consider is sort of this instinctual understanding that I think a lot of what colleges try to teach can be hard without experience. So, and that's where you get that when you have a real world experience and then later come back and you just have to tie in theoretical. I think it's easier to tie in theoretical once you have the real world experience versus the other way. At least that's what I felt going through.
And I guess as a graduate student, because a PhD is different from the undergrad part of it, is there anything that you think that brought you as you had to think about this, running your own research project and dealing with the problems and roadblocks that come up along the way?
Definitely. So on that side of things, so the PhD is different, right? So the point of a PhD is you're looking at something fundamentally different and never done before, making what we call the little notch in the circle of knowledge that's just hasn't been studied before. And so in that case, what I relied on from my past experience was just the structure that I learned along the way. And by structure, I mean, structure of your day, time management on certain projects, which I notice is hard in meeting the deadlines and pushing that project along and knowing where and when you need to stop pushing on one thing because it's reached a certain acceptable limit and going to the next thing and sort of putting all the pieces together before you refine it. And so it's just building that structure. I did have a hard time, I'd say, part of my PhD wasn't during COVID. And so I did have a hard time working from home. I'm not a big work from home person because, again, part of that structure for me is going into work. I have a really hard shift in mentality from at home to working at work and then going back home. It was just inherent in me. And so I think that's definitely what helped me. And a successful PhD is all that structure that I already had in place.
Is there anything that we haven't talked about that you think is important to mention about your science, about your career path?
Just in general, I think I like the idea that the flexibility and everything like the CFGF allows and the PhD in general is that it sort of anyone can achieve their PhD. And so I'm not sure if I mentioned it earlier yet or not, but I was growing a family outside of the PhD. And so it's possible for anybody to do. And so anyone that listens and thinks they're sort of lost in this PhD world, because it can be very drowning sometimes with all these deadlines and stuff, just know there is always a light at the end of the tunnel and you can manage it and you can definitely achieve whatever you need to achieve.
If you wanted to pass along a nugget of advice for an early career researcher or someone behind you, or maybe somebody who's coming in as a non-traditional student, what words of wisdom would you pass along?
My advice is definitely build that structure in your life, because a routine really helps keep things in line. So you always know, you can always expect what's next, because there's a lot of work associated with the PhD. And so if you can just set that routine of doing the same thing, the simple things every day, then all the hard things sort of fall into place as well. And so you build that structure in your life. And then what I sort of associate it with is, I forget the reference, but it takes 10,000 hours to master a task. And if you break it down for 10,000 hours, if you do 9-hour days, it takes about 5 years to master whatever you're looking at. And that's about the same timeline as a PhD, which I thought was an interesting coincidence. So if you just structure out that 9 hours, 5 days a week, and work towards and realize it's a long-term thing and not like you're always thinking about the next deadline, which seems so short, and then you never realize that this is playing the long game, and getting to the PhD takes 5 years. And so take a deep breath, build that structure and timeline in your day, and you'll definitely succeed.
That sounds like a wonderful place to end. Stephen, thank you so much. It's been such a pleasure.
Thank you so much for having me.
To learn more about Stephen Wilson's research and the quantum chemistry startup SciForge, please check out our show notes at scienceinparallel.org. Science in Parallel is produced by the Krell Institute and is a media project of the Department of Energy Computational Science Graduate Fellowship Program. Any opinions expressed are those of the speaker and not those of their employers, the Krell Institute, or the U.S. Department of Energy. Our music is by Steve O'Reilly. This episode was written and produced by Sarah Webb and edited by Susan Fallett.